So I'm going to tell you about shortcut graphs and groups. So shortcut graphs are graphs satisfying a very weak form of non-positive curvature. And it turns out that there are many examples in the geometric group theory and metric graph theory literature, yet the conditions are strong enough to have still some consequences on the groups that are acting on these graphs. So before I get into the definition, I'll say a few motivating words. Starting with this, the following observation, that circles don't embed in Euclidean spaces. And what I mean by that is that if F is a one Lipschitz map from a circle into a Euclidean space, then there's going to be some pair of antipodal points in S1, P and P bar, that are closer in the Euclidean space than they are in the circle, and in fact closer by a constant factor of 2 over pi. And in the case of a perfectly round circle in the plane, that's the case for every pair of antipodal points, is that they're at distance 2 over pi. On the other hand, circles do isometrically embed in spheres. So any great circle in a sphere is isometrically embedded. So this suggests that this is that this cycle distortion is a phenomenon that's related to non-positive curvature. So the other bit of motivation I wanted to share comes from the world of combinatorial non-positive curvature. So systolic and quadratic complexes are complexes that have showed up in the metric graph theory literature and in the for their metric properties, and in the geometric group theory literature for their interactions with the groups that act on them and the consequences that they have for the groups that act on them. Much the same as cat-sphere cube complexes have also appeared in those two fields. So I won't give a definition, but here are two examples. And I bring these classes of complexes up because of a pair of analogous theorems. So the first is the theorem of Victor Chapoy. It says that simplicial complex X is systolic if and only if it is flag, and every isometrically embedded cycle in its one skeleton has length 3. So so assuming the one skeleton is, so the one skeleton is a simple graph. So what we're being told is that the only kinds of cycles you see that are isometrically embedded are the shortest possible ones of length 3. And since this flagness condition is something that just tells you how to recover the higher dimensional cells, it's really this condition on cycles that characterizes the graph space. Completely analogously, in the case of quadratic complexes, we have this theorem of mine that says that square complex is quadratic if and only if it's square flag, and every isometrically embedded cycle in its one skeleton has length 4. So square flag here again just tells you which squares to glue in, the main characterizing condition is this one about isometrically embedded cycles all having length 4. And so in the case of bipartite graphs and sort of any simply connected two complex built out of squares is going to have a one skeleton that's bipartite. 4 is the shortest length of a cycle that that you can have. Well, okay, assuming no multi-edges. So yeah, so we see that so we had one bit of motivation from a continuous setting, and here we see that also in the world of combinatorial non-positive curvature, cycle distortion seems to show up prominently. Yeah, so some natural questions arise, at least for me, from these from that bit of discussion. Are there other classes of combinatorial non-positively curved spaces that satisfy similar cycle distortion properties? I've already suggested that the answer is yes. And are there general consequences of cycle distortion properties, which we'll also look into? Yeah. So the purpose of the talk is to partially address these two questions. Okay, so just to make sure we're on the right page, just a bit of preliminary discussion on terms. So we're going to view, for this talk, we're going to view graphs as geodesic metric spaces with edges isometric to the unit interval. For example, the cycle graph on n vertices, Cn, is isometric to S1 with a geodesic metric of length n. A cycle in a graph is a graph homomorphism from a cycle graph, Cn, to gamma. Okay, sometimes this is called a closed walk. And a cycle is isometric, or cycle in a graph is isometric if it is an isometric embedding when viewed as a map of metric spaces. Okay, so you have a continuous map between two geodesic metric spaces, then it's an isometric cycle if this map is an isometric embedding. Okay, so just a quick little example. So here we have an n by n grid graph. It's like a piece of the standard Cayley graph of z squared. The boundary here is a cycle graph, and its its inclusion is not an isometric cycle, because we have a pair of vertices here, this guy and this guy, that in the cycle they're at distance 8, but in the codomain, in this ambient graph, they're at distance 4 from each other. Whereas if we were to subdivide each of the edges not in the image of the cycle, then in the resulting situation, the cycle would be isometrically embedded. So, okay. Okay, so we're ready to start giving our main definitions now. A shortcut graph is a graph for which there's a bound on the lengths of its isometric cycles. So in other words, there's some bound theta, and any cycle in the graph that's longer than theta is not going to be isometrically embedded. So there's going to be some pair of points that are closer in the graph than they were in the cycle. So I'll point something out here now, that a cycle F is isometric if and only if, just when looking at antipodal pairs of points, P and P bar, the images F of P and F of P bar are at distance at least C/2, at least half the length of the cycle. Of course, cycles are one Lipschitz maps, and P and P bar are at distance C/2 in the cycle. So in fact, what you get is equality there. But I write it this way to help motivate the next definition, we're going to say that a cycle is psi almost isometric for some psi between 0 and 1 if for any pair of antipodal points, P and P bar, their distance in the graph is at least psi times half the length of the cycle. So using this notion, it's kind of like being you know, it's kind of like being by Lipschitz, I guess, but you only care about antipodal pairs of points. So with that, we can give the definition of strongly shortcut. But maybe I'll just go back to the previous slide for a second. So this example here on the left again, which we said is not isometrically embedded, it is 1/2 almost isometrically embedded, because the worst distortion factor we get is between this point and this point, and that's a distortion of 1/2. But it's not 1/2 plus epsilon almost isometrically embedded for any epsilon greater than 0. Okay, so a strongly shortcut graph is a graph gamma such that for some psi, now strictly between 0 and 1, there's a bound on the lengths of the psi almost isometric cycles of gamma. Okay, so we're not just bounding isometric cycles, even cycles that are close enough to being isometric are also bounded in length. And yeah, so notice that if we allowed psi to be 1, then you know, psi almost isometric is the same as isometric. So 1 almost isometric cycle is an isometric cycle. So yeah, so in that sense, the two notions are you know, can be viewed in a similar light that way. Right. So the talk is about shortcut graphs and groups. So groups do have to come up at some point. A group is a shortcut or strongly shortcut if it acts properly and co-compactly on a shortcut or strongly shortcut graph, respectively. Okay, so I like to tell you about a different characterization of strongly shortcut graphs, and this is one that comes up in Hume and McKay's work on separation profiles, where they use it to characterize hyperbolicity, and I'll talk a little bit more about that later in the talk. So the characterization goes as follows. Gamma is strongly shortcut if and only if, for some k strictly greater than 1, there's a bound on the lengths of the k by Lipschitz cycles of gamma. So the forward direction here is pretty immediate, because if we take k equals 1 over psi, and gamma is strongly shortcut, then any k by Lipschitz cycle is also going to be psi almost isometric. In fact, it's going to be even better than psi almost isometric, because the k by Lipschitz property is satisfied for all pairs of points. It's not just about antipodal pairs. And so the length of that cycle, that k by Lipschitz cycle, would have to be bounded by the same bound that bounds the lengths of psi almost isometric cycles of gamma. So the interesting direction is the reverse direction, and the way that goes, I mean, what we want to show is that if you have psi, you know, if you're not strongly shortcut, so that would mean that you have cycles of arbitrarily long length that are psi almost isometric for psi arbitrarily close to 1, then we want to be able to construct cycles of arbitrarily large length there are k by Lipschitz for k arbitrarily close to 1. And that's done by performing little surgeries. So the difference between a k by Lipschitz cycle and a psi almost isometric cycle is that the k by Lipschitz property can fail locally. So you can have a cycle that's very nicely embedded, but maybe two nearby vertices are mapped to the same point. And that's sort of now that's not going to be a by Lipschitz embedded cycle because it's not embedded, but it could be psi almost isometric for very good psi. So we take our psi almost isometric cycle, of which we have this family of arbitrarily large length and arbitrarily good psi, we find segments that are not k by Lipschitz embedded for k some function of psi. Okay, so we replace those segments with geodesics between their endpoints. So we snip off these little bits that aren't k by Lipschitz and replace them. And because of the cycle being k almost isometrically embedded, being psi almost isometrically embedded for a very good value of psi relative to 1 over k, these segments have to be very short. And they don't interact with each other, and so because things are getting shorter and shorter, this process eventually, the cycle is getting shorter and shorter. The process eventually terminates, and you can also you can show that the sum of the lengths was of the segments that you replaced were short relative to the length of the cycle, and so the k by Lipschitz cycle that you end up with is long, is at least a constant factor times the length of the original cycle. And so using this, you can construct that family of cycles of arbitrarily large length that are k by Lipschitz for arbitrarily good k. All right, so let's start talking about some properties that have group theoretic consequences. Okay. Yeah, so let gamma be a shortcut graph or a strongly shortcut graph, and let theta bound the lengths of the psi almost isometric cycles of gamma. So here psi is between 0 and 1, with 1 allowed in the case that gamma is shortcut but not strongly shortcut. So we're going to construct a 2 complex from gamma by gluing in a 2 cell along each cycle of length at most theta. And then the conclusion is that this 2 complex f sub theta of gamma is simply connected. To prove this, we're going to construct a disk diagram for an arbitrary given cycle by induction on the length of C. So of course, if C is short enough, then C already bounds a 2 cell. So we have a disk diagram for C of area 1, having a single 2 cell. Otherwise, if C is long, then there's going to be some pair of vertices that are nearly antipodal. So these aren't just points; they're actual vertices. They may be off by 1 or 2 from being antipodal. But they're going to be closer in the graph than they are in the cycle, and closer in the strong shortcut case. They're going to be closer by a psi factor. Now these 2 points U and V, they separate our cycle C into 2 segments, call them A and B, and we're going to let P to gamma be a geodesic between U and V. So then this computation shows that the new cycles that we get here, A union P and B union P, well, they're going to be strictly shorter than C. And in the strong shortcut case, they're going to be shorter by a constant factor. Okay, so then by induction, we have disk diagrams for A union P and B union P, and so we can glue those together to get a disk diagram for C, and so we're done. So we see that C is null homotopic. Okay, so actually, as a consequence of the proof, we get a little bit more. What the computation showed is that during the inductive step, we're replacing our cycle with two shorter cycles. So what we get is that f sub theta of gamma has at most exponential Dane function. So that's just the shortcut case, and if psi is strictly less than 1, and so that's the strong shortcut case, then f sub theta of gamma has at most polynomial Dane function. And it's just by the recurrence relation that you get from that inductive step. You know, either you're replacing your cycle with two that are strictly shorter, or you're replacing your cycle with two that are shorter by a constant factor, and those recurrence, solving those recurrence relations, you get either the exponential or the polynomial bound. The other corollary we get is that shortcut groups are finitely presentable and have decidable word problem. Okay, let's talk about some examples from geometric group theory. So we can show that these classes of groups are all strongly shortcut. So hyperbolic, these classes of graphs. Hyperbolic graphs are strongly shortcut. That's not too hard to see, especially using the characterization, the K by Lipschitz characterization of the strong shortcut property. So if you have a K by Lipschitz cycle in a hyperbolic graph, you can subdivide it into two K by Lipschitz paths between a pair of antipodes. And these paths are quasi-geodesic, so using the Morse lemma, they have to fellow travel a geodesic. And so then you see that if you travel along them halfway, you're going to be obtain two antipodes that are very close to each other by a constant. And so the only way, since the cycle is K by Lipschitz, it would have had to be very short. Using a different argument, you can show that in fact they're strongly shortcut with for any psi greater than 1/3. So one way to see that is using the asymptotic cone, which is always a tree for a hyperbolic graph. Also, the one skeleton of finite dimensional cat-zero cube complexes are all strongly shortcut. That requires a more involved argument using combinatorics of walls and how the walls interact with distance in the one skeleton, and also a bit of some tools from combinatorics like Taran's theorem. And a result of Niblo and Reeves then automatically implies that the standard Cayley graphs of finitely generated Coxeter groups are strongly shortcut, because their cubulation gives an isometric embedding of these Cayley graphs into finite dimensional one skeleton of finite dimensional cat-zero cube complexes, and so then that follows from that. Also, every Cayley graph of Z and Z squared is a strongly shortcut, and in fact, with Piotr Pajitsky, we extended this, showed that it holds for every calligraph of z to the n for all n. This kind of somewhat suggests that maybe it's possible that the strong shortcut property is invariant under change of generating sets. As a property of graphs, it's not a quasi-isometry invariant. It would be interesting if for groups, the property is invariant under change of generating set. But the next example shows that the shortcut property is definitely not invariant for calligraphs under change of generating set. So the Baum-Slack-Solitar group BS12 is in fact shortcut. Its standard calligraph is shortcut. But of course, BS12 has exponential Dane function, so it can't be strongly shortcut. So that's a group that's shortcut but not strongly shortcut. But on top of that, BS12 also has a calligraph that's not shortcut. So we see there that we don't have invariance of the shortcut property under change of generating sets. Okay. And the last thing I wanted to tell you about is that it turns out there's actually a psi. So we've seen that strongly shortcut groups don't have to be hyperbolic. Of course, we see also all sorts of examples that are not hyperbolic. But it turns out that there is a psi such that if gamma is strongly shortcut with this psi, then it's hyperbolic, and then that's if and only if, because because there exists this psi that's greater than 1/3. So right. So this holds for any psi strictly between 1/3 and √2 - 1. Of course, it doesn't hold for psi equals 1/2 because the calligraph standard calligraph of z² is not hyperbolic. And yet it's strongly shortcut for psi equals 1/2. So it's not known if what the tight value here is at the top of this interval. But that could be an interesting thing to figure out. And it's interesting to compare this result to the result of Hume and McKay, that any graph for which there's a bound on the lengths of its 18 by Lipschitz cycles is hyperbolic, and that the converse also holds there as well. So it's not exactly possible to convert between these numbers, because the proof relating or characterizing strong shortcut in terms of k by Lipschitz cycles isn't perfectly numerical in that way. But yeah, so there are this pair of related ways of characterizing hyperbolicity. And that's about all that I have to say. So thank you for listening.